Hello all, welcome to the second lecture of this course on fluid mechanics. In the previous session, we have seen what is fluid mechanics and what type of studies are involved in fluid mechanics. Further, we have also discussed about the application areas of fluid mechanics in engineering field with the help of few real life examples. At the end, we have discussed a brief objectives of this course on fluid mechanics. So let us now get into the subject. So today's session includes the technical definition of fluid. Further, we will also talk about how does a solid and a fluid matter differs from each other. And finally, in this session, I will introduce you with a few important fluid properties. We have been studying from our school days that the substance usually exists in one out of the three primary phases. They are a solid, a liquid, and a gas. Obviously, in the fourth, that is plasma, which exists at very high temperature. As discussed briefly in the previous session, that all the substance in a liquid or a gas form are considered to be the fluid. So since we said that a fluid is a substance that can flow, for example, that is a fluid is a substance that can flow, for example, a water, a milk, a fruit juice, then the oxygen that we breathe in, and CNG gas, and many more. At the first glance, a definition of fluid is fine, but when someone is interested in learning the mechanics of a fluid body in detail, one has to understand the fluid from a deeper and technical perspective. So now we will try to understand a fluid and make an attempt to provide its fundamental and technical definition. Say for instance, before defining a fluid technically, let us understand a few terminologies here. So you will recall from the statics that a stress is defined as force per unit area and is determined by dividing the force by the area upon which it acts. So let us consider a surface of a liquid. On that surface, let us consider a small area dA, very small area dA. Then the normal component of the force acting on the surface per unit area is called the normal stress, where Fn here represents this Fn represents the normal to the surface, the force acting normal to the surface of area dA, and Ft represents the tangential force acting on the surface which is parallel to the surface area of dA. This is called tangent to the surface, a tangential force, and the resultant force is called as a force which is acting on area dA, that is force F acting on an area dA. So here the normal component of the force Fn acting on the surface per unit area is called as a normal stress, and the tangential component of the force acting on the surface per unit area is called as a tangential stress or shear stress. In a fluid at rest, if you take in a fluid at rest, the normal stress is called the pressure, and a fluid at rest is at a zero shear stress. If the fluid is at rest condition, it is having a zero shear stress, and at the fluid at rest, the only force acting on the fluid will be the normal stress, and that is called as a pressure. When walls of the container are removed, when the walls of the container are removed or a liquid container is tilted, a shear develops as the liquid moves to re-establish a horizontal free surface. So here look at this is a liquid and this is a liquid filled in a container. When the walls of this container are removed or just you tilt sideward, a liquid starts deforming continuously. Okay. Even gas which will expand widely the surface. Okay. So this is about a few terminologies, that is a normal stress, tangential stress, and the stress. So here the normal stress is nothing but normal force divided by area. Tangential stress or the shear stress is nothing but tangential force upon area. And when the fluid is at rest condition, the shear stress will be zero here. When the fluid is at rest, the shear stress acting on the fluid will be zero, and the only force acting is the pressure, that is normal stress. So that's why it is given here, the normal stress and the shear stress at the surface of the fluid element. That is, for a fluid at rest, the shear stress is zero and the pressure is the only normal stress. Now say for instance we have two flat plates. An upper plate here, this is the upper plate, and the lower plate. Now we have a solid matter, say a rubber, which is tightly held between these two plates. So looking from the front, we observe this arrangement to be like this. So if when you look from the front, we observe this arrangement will be like this. Means the upper plate and the lower plate, in between the plate a rubber is been held. Here this is the rubber is been held. This is a solid object and the force is being applying. Let us apply a force F of a certain specific magnitude to the upper plate in horizontal direction. Due to this horizontal force, the rubber that is held tightly between the two plates will start deforming and eventually will acquire a new shape. Look at this one. So when the force is being applying on the upper plate, this rubber will get deformed, and this is the deformed shape of the rubber. So this rubber will acquire a new shape. So the magnitude of the deformation can be measured. So this is the magnitude of the deformation can be measured by an angle, say beta. So this is the magnitude of the angle. This is beta. So that the rubber will remain in this deformed shape until a force F is acting on this plate. The moment we release this force F, the rubber will partially or fully regain its original shape. Then the applied force is sometimes also known as shear force. This applied force is sometimes also known as shear force. This is the applied force. Sometimes is also known as shear force, since its line of action is parallel to the upper plane. Since its line of action parallel to the upper plane of the rubber, then the angle of deformation is directly proportional to the applied force on the upper plate. So more the magnitude of the force, more is the deformation. So more the magnitude of force, more is the deformation. For the applied force, a rubber will get deformed, and this is the deformed shape of the rubber, and it will resist the deformation by the force by deforming a certain angle that is called as a beta. In here it is calling as a shear strain. And here we have marked the contact area between the rubber and the plate. Okay, so as I said, more the magnitude of the force, more is the deformation. So let us now try to understand this concept with the help of some random numbers here. Let us try to understand the concept of this deformation under the action of force when the rubber is held between the plates. Try to understand this concept with the help of some random number. Say that we have applied a 1 Newton of a force here. Say that we have applied a 1 Newton of force, or the 1 Newton of shear force. And under the influence of this 1 Newton of shear force, the angular deformation here, the beta, the angular deformation that has taken place is observed to be 3 degrees. For the under the influence of 1 Newton of force, when we have applied here 1 Newton of force, when we applied here, then the deformation that we are observing here, that is beta, we have observed here as a 3 degrees. So that this means 1 Newton of shear force corresponding to 3 degrees of deformation. 1 Newton of shear force corresponding to 3 degrees of deformation. Let us now increase the magnitude of this force, say by 2 Newton. Again, increase it by 2 Newton. So under the action of 2 Newton of force, the angular deformation will be how much? 6 degrees. The angular deformation will be 6 degrees. That means, so under the action of 2 Newton of force, the angular deformation will increases, and it will be 6 degrees. And further increase of shear force, say 5 Newton, we're increasing again further 5 Newton here. We're increasing the force 5 Newton. The angular deformation will even further increases, and it will be 15 degrees. So therefore, so from this we can conclude that. So what we can conclude here? Therefore, the amount of total angular deformation of a solid body, the amount of total angular deformation of a solid body is directly proportional to the magnitude of the shear force applied. I'll repeat once again. The amount of total angular deformation, that is beta, of a solid body is directly proportional to the magnitude of the shear force applied. So this is the explanation of this concept of a rubber held between the two plates. Now, if these experiments were repeated with a fluid substance, let us take a fluid is held between the two plates. So previous one was a solid was held between the plates, and for that we have seen the deformation, and we have made the conclusion that that deformation is directly proportional to the force applied on the upper surface of the rubber. Now, if these experiments were repeated with the help of a fluid substance, so let us take a fluid as a water between the plates. So consider the upper plate and the lower plate. So the lower plate is considered the fixed one, this plate is a fixed one, and the upper plate is movable. Again, see, the water is held between the plates. And what would happen? Let us look at it. Consider a fluid medium, say water, placed between the two large plates, and again apply a force F to the upper plate. Hence, the upper plate will start moving, and unlike a solid, the body of the plate here will not come to the rest even after a certain amount of displacement. Okay. So here, when we are looking from the front side, it looks like this. Then here the force is being applying on the upper side of the plate, that is a force F to the upper plate. Hence, what will happen here? The upper plate will start moving, and unlike a solid body, the plate here will not come to rest even after certain amount of displacement. Okay, this is the displacement. Again the same, the contact area between the fluid particle and the plate, and this is the shear stress acting on the surface, that is interface between the plate and the fluid body, and the plate is moving at a velocity of v meter per second. Then we get the rate of shear strain here. So it will what will happen here when the F, that is the force F to the upper plate, and the upper plate will start moving, and unlike as I said, unlike a solid body, the plate here will not come to the rest even after the certain amount of displacement, and it will keep on moving a particular speed. This will be keep on moving at a particular speed, say v meter per second, and therefore the fluid element will keep on deforming continuously at a particular rate till the force F is acting. So here we can say the rate at which the fluid is deforming is characterized. The rate at which the fluid is deforming is characterized by d beta by dt, which indicates that the amount of angular deformation or rate of shear strain is proportional to the magnitude of shear force applied. I'll repeat. This indicates that the amount of angular deformation, the rate at which the fluid is deforming is characterized by d beta by dt, which indicates that the amount of angular deformation in 1 second. The amount of angular deformation in 1 second. Here the rate of angular deformation is proportional to the magnitude of shear force applied. So let us try to understand again this with the help of some random numbers. So let us try to understand this concept with the help of some random numbers I'm taking here. Say for instance we have applied 1 Newton of shear force. Here we have applied 1 Newton of shear force. Again start applying 1 Newton of shear force. 1 Newton of shear force, and under the action of this force the rate of angular deformation is bound to be 4 degrees per second. Here I am taking 4 degrees per second. Here 4 degrees per second, which means that water will keep on deforming by 4 degrees. Water will keep on deforming by 4 degrees in 1 second until 1 Newton of force is applied. Until 1 Newton of force is applied. When we increase the force, say by 3 Newton, the rate of deformation will again increases and will be equal to 12 degrees per second. So which means in case of a fluid, the shear force is proportional to the rate of angular deformation, or you can call it as a rate of shear strain. Even at a very low magnitude of shear force, say about 0.001 Newton, the deformation even at a very low magnitude of shear force would be 0.004. That is, angular deformation would be 0.004 degrees per second. Therefore, a fluid is technically defined as, now we can define a fluid is technically defined as, what is that? A substance. Now, the fluid is technically defined as a substance that deforms. A fluid is technically defined as a substance that deforms continuously under the influence of shear stress, no matter how small the force may be. So this is the technical definition of a fluid. So let us now summarize this discussion by listing down the key differences in the behavior of a solid and a fluid. Now let us differentiate between a solid and fluid based on the ability to resist the external forces. So we have seen the two experiments. So one, when the solid was held between the two plates, that is upper and lower plates, and when in case of a fluid, when the liquid is held between the fluid is held between the upper plate and the lower plate. So with this experiment we can differentiate between a solid and fluid. So in case of a solid, under the action of shear force, that is a shear force of a solid body, under the action of this shear force, a solid body deforms by a certain angle. The body will remain in the deformed state, resisting the applied shear force. Therefore a solid body can resist the shear force under the static condition. I'll repeat once again. Under the action of shear force, a solid body deforms by an angle of beta. This is the deformation angle. It is deforms by a certain angle. Then the body will remain in this deformed state, resisting the shear force, resisting the applied shear force. Therefore, a solid body, we can say, the solid body can resist a shear force under the static condition. Then, whereas on contrary, a fluid body keeps on deforming continuously under the action of shear force. Therefore, a fluid, we can say, a fluid cannot resist shear force under static condition. This is the first difference we can make between a solid and a fluid. So a solid which resists a shear force under static condition, whereas A fluid cannot resist shear force under static condition. Second difference, solids do not keep on deforming continuously under the action of shear force, whereas a fluid do keep on deforming continuously under the action of shear force. This is the second difference we can make. Third difference, a solid can regain its original shape fully or partially when the shear force is removed. Means if you remove this force, okay, so if it is a within elastic limit, the force is within elastic limit, the solid can regain its original shape and size, okay, or it may come back to its original shape fully, or it may come back partially also. But whereas a fluid can never regain, see, this is very important, a fluid can never regain its original shape when the shear force is removed. Okay, so these are the few differences you can make, that is based on the forces applied on the surface of solid as well as on fluid. Then further we can make a difference between a solids, liquids and gas based on certain parameters. So look at this picture here. So the first one is a solid, second a liquid and a gases. So we can make a certain parameters like arrangement of molecules, how the arrangement of molecules in a solids, and even position of the molecules in the solids or liquids and the gases, and the movement of molecules in the solids, liquids and the gases. Like this we can make differences between the solids, liquids and the gases. So if you look at the arrangement of molecules in case of a solids, they are very closely packed. They are very closely packed. In case of a liquids, the molecules are loosely packed as compared to the solids. If you take the gases, they are placed very apart from each other when you compare it with the liquids. So the molecules are very far away from each other. Then if you take the position of the molecules in case of solids, the positions are fixed here. They are not placed randomly. They are fixed position. They are having a fixed position. So in case of a liquids, the greater freedom of movement will be there for us liquids. That's why the liquid can be transferring from one container to the other container. And in case of a gases, if you take here, they are having a maximum freedom of motion. And next you can take the moment of molecules. The moment of molecules, if you are considering in case of a solids, it is very less. If you apply a force, the very little movement we can observe in case of a solids, they or sometimes they may not move also. Okay, so it is, you can say it is very less, due to which solids possess a rigid and compact form. But in case of a liquids, the molecules move freely. However, force of attraction is sufficient to keep the molecules together to occupy definite volume. But whereas in case of a gases, move independently, or you can get randomly, hence occupy the container in which they are filled, gases. Then the density, based on the density, if you want to differentiate, the density for a solid is very high, and for liquids it is lower than the solids. We can say less, that is lower than the solids, and but greater than the gases. And gases, if you take, they are having a very low densities compared to the liquid. Then the shape and volume. So based on the shape and volume, if you want to differentiate between a solids, liquid and gas, solids will have a definite shape and size, or you can say definite shape and definite volume, whereas liquids they are indefinite shape, but they will be having a definite volume, but gases, if you take indefinite shape and indefinite volume, you can say here neither the definite volume nor the definite shape. Then again, the solids are more strong. They are having a strong attraction between the particles, that is a cohesive force is more strong. But in case of a liquids, moderate attraction between the particles. Compared to solids, they will be having a moderate attraction between the particles, that is a cohesive force. So in case of a gases, the cohesive force is very weak, that is very weak attraction between the particles. And in case of a solids, if you take particles are very close together and neatly arranged, so here the neatly arranged, particles still very close together but not neatly arranged. Particles are much further away from each other. Okay. Then particles vibrate in a place, means they do not move here and there. They vibrate in their own place only. Okay. So if you take a liquids, particles are able to slide past each other. If you just tilt a liquid held in a container, if you just tilt it sideward, they move faster. Okay, they vibrate. They want to vibrate in a place, they move sideward. The particles move all around and bump into each other in case of the gases. And if you again still differentiating based on the ability to resist external forces, the solids will resist all kind of forces like a tensile, compressive and shear forces. But if you take a liquids, no resistance to tension forces, they won't resist any tensile force here, but supports compressive force when placed in a container. Under the shear, the fluid particles continuously deform. Gases, no tensile strength for gases, but can be compressed very well. Okay. So these are the few differences of solids, liquids and gases. Means based on the molecular arrangement, based on the moment of molecules, density, shape and volume, force of attraction between the molecules, or ability to resist the external forces, you can make the differences between the solids, liquids and gases. Okay. I hope you understood this differentiation. Now coming to the fluid properties. The fluid possesses certain properties like a mass density, specific weight, specific volume, specific gravity, viscosity or dynamic viscosity, kinematic viscosity, bulk modulus of elasticity, coefficient of compressibility, coefficient of volume expansion, surface tension and capillarity. So these all are the properties of the fluid. Okay, so let us discuss one by one the properties of fluid. Let us take the first property, mass density. So here we are going to define what is mass density, or it is also called as specific mass. And let us first define what is mass. What is mass? The mass of an object is a measure of how heavy or how light the object is. And generally the unit of mass, the mass can be measured in terms of a grams, which is used to measure a lighter object. Sometimes the mass is measured in terms of a grams or kgs. Heavier, this unit is used to measure heavier objects, or heavier weights are measured. And how the mass density can be defined? The mass density of a fluid is the mass of the fluid occupied in a unit volume. So mass of a fluid occupied in a unit volume. So we can write mathematically the mass density as mass by volume. So let us consider a container having a width 1 meter, height 1 meter, length 1 meter, height 1 meter and a width 1 meter. So this is 1 cubic meter of a container. So its volume is 1 meter cube. Length, breadth and height. If you fill this container by a liquid, so it is filled. Now we can easily define the density of this container, that is mass. If you weigh this container by keeping on the weighing machine, so suppose the mass weighs 1000 kg. The mass of this container is 1000 kg. Okay, then we can say the density of water is, you can say 1000 kg per meter cube. That is a fluid, that is means the mass of a fluid occupied in a unit volume. Unit volume is 1 meter cube. The mass of this fluid occupied in a 1 meter cube of volume, that is called as density. So that is called as density of water. So 1 kg of mass occupied in 1 meter cube. Okay, so the mass density is sometimes also known as density or specific mass. So its unit is kg per meter cube. So it's a SI system, SI unit. And even if you take in place of a water, if you are taking a mercury, again the same volume we are taking, and if you fill the container uh, with mercury, so the container is filling by mercury. Again, if you weigh the mercury, suppose if it is weighing, say if it is weighing, its mass is 13,600 kgs. It means the density of mercury is 13,600 kg per meter cube. 13,600 kg per meter cube. Again, the unit of mass density will be kg per meter. So that the density of liquid may be constant, but the density of gases changes with the variation of temperature and pressure. Since the mass of fluid depends upon the number of molecules in a given volume, so mass density decreases with increase in temperature, while it increases with increase in pressure. But the density of gases changes with the variation of temperature and pressure. So the density of water is 1000 kg per meter cube, or we can say 1 gram per centimeter cube, or 1 gram per cc. Mathematically, we can write the density as mass of fluid divided by volume of fluid. At 4 degrees Celsius, if you take the water density 1000 kg per meter cube, and this is the maximum. So always remember, the density of water will be 1000 kg per meter cube, always 1000 kg per meter cube, 1000 kg per meter cube. So as the temperature increases, the molecules will move away and density increases. As the temperature increases, the molecules will move away and density decreases. This is decreases. Density decreases. Let us take the second property, the specific weight. So it can be defined as, and it is represented with symbol gamma. It can be defined as the weight of the fluid occupied in a unit volume. The weight of the fluid occupied in a unit volume. Again, the specific weight can be defined as mathematically weight by volume. So weight is nothing but the mass into acceleration due to gravity. That is how the weight can be defined. The force of gravity which is acting upon a mass. The force of gravity which acting upon a mass is called as a weight. That is m into g divided by volume. But what is mass by volume is a density. Okay, so we can write the specific weight of a water, gamma w. So m into g by v, that is 1000 into 9.81 divided by volume is 1. So again the volume to be taken, container volume, as 1 meter cube. So now if you weight, the mass is 1000 kg, but on this mass there is a force of gravity which is acting, and then when the mass is multiplied by g, then it becomes a weight. Then the weight by volume is nothing but specific weight. So again, if you weigh the mercury, again it weighs at 13,600 kg, but when you multiply it by g, it will become a weight. Hence a specific weight of water can be written 9810 Newton per meter cube, because 1000, this is a kg, and this one is a meter per second square, that is g, acceleration due to gravity, and this is meter cube. Then the kg meter per second square is nothing but Newton. So the unit finally we get as a Newton per meter cube. And in 1 meter cube volume of a container, the weight of the fluid will be 9810 Newton. Hence the specific weight of water is nothing but density into gravitational acceleration. Why the density? Because mass by volume, we know that it is a density, rho into g. That's why the specific weight of water, gamma w, is the density into gravitational acceleration. So hence the SI unit of specific weight will be Newton per meter cube. So let us take the next property of a fluid, that is the specific volume. So specific volume is the amount of volume of a fluid occupied in a unit mass of a fluid. Amount of volume of a fluid occupied by unit mass of fluid. That is, specific volume is volume by mass, or we can take the specific volume is the reciprocal of the mass density. So again we are taking the volume of volume as 1 meter cube volume. The specific volume of water will be the 1 meter cube by 1000. Or how it can be defined, the specific volume as, specific volume is a property of a material defined as the number of cubic meters cubic meters occupied, the number of cubic meters occupied by 1 kilogram of particular substance. 1 kilogram of a particular substance. 1 kilogram of particular substance. And that's why its unit is meter cube per kg. Meter cube per kg we write. Okay, so because density unit is kg per meter cube, is the reciprocal of density means meter cube per kg. That is specific volume. Specific volume is inversely proportional to the density. Inversely proportional to the density. Hence, the specific volume is defined as the ratio of volume of fluid by mass of fluid. Mass of fluid. In the same. Okay. So, how it can be understood the specific volume? So, imagine a variable volume airtight chamber like this. Imagine a variable volume of airtight chamber containing a certain number of atoms of oxygen in it. Certain number of atoms of oxygen in it. It has contains atoms, gas molecules. Consider on the basis of the molecules contained in the container. If suppose this chamber is made smaller, suppose this chamber size if we have reduced, it is made smaller without allowing a gas in or out, the density increases and specific volume decreases. When you reduce the volume of this container, what will happen? These molecules will come closer and closer. Its density get increases, but whereas this volume get decreases. Okay. The second case, if you take, if the chamber expands, suppose if you have made this chamber large, if this chamber expands without letting the gas in or out, so what will happen? These gas molecules will get expanded, they move away from each other, the density decreases and the specific volume increases. Okay, this is how we can understand the specific volume and density, how they are related to each other. If third case, if you want to take, if the size of the chamber remains constant, if this size remains constant and new atoms of gas are injected, if you again add some more atoms into this container, what will happen? The density get increases, means the molecules will come closer and closer because you are allowing or you are injecting some of the molecules into it, because the chamber sizes you are kept constant, the chamber size you are kept constant, the density increases, the specific volume of this container get decreases. Hence we can say the specific volume is inversely proportional to the density. As the density decreases, the specific volume increases. As the density increases, the specific volume decreases. Okay, its unit is meter cube per kg. And that's why the definition of the specific volume is what? The number of cubic meter occupied. The number of cubic meter occupied by 1 kg of a particular substance is nothing but as a specific volume. Okay, its SI unit is meter cube per kg, or 1 meter cube equal to 1000 liters, or you can say 1 liter equal to 1 kg. So next, very important definition is specific gravity. It is defined as the ratio of weight of a given fluid to the weight of a standard fluid of volume equal to the volume of fluid. So how we can define the specific gravity of fluid X is equal to the density of fluid X divided by density of standard fluid. So here the standard fluid to be taken as a water. It is for a liquid, it is to be taken as a water, and for a gaseous air is to be taken as a standard fluid. So it is the ratio of density of any fluid divided by density of standard fluid. And this specific gravity can be used to identify unknown compounds and even immediately to determine if object floats and measures it can be identified which objects will float on the surface of water or which objects will sink into the liquid based on the specific gravity, we can say. So these are the some fluid properties. These 4 properties we have discussed, that is mass density, then specific weight, then specific volume and specific gravity. Okay, the unit of the specific gravity is unitless. Its unit is, there is no unit, it doesn't have any unit. Okay, because it is the ratio of 2 densities. Sometimes the specific gravity is also called as a relative density. Remember, relative density, relative density. Why it is calling as a relative density? Because it compares two densities of fluid. See, the density of any fluid divided by density of standard fluid. Density kg per meter cube, density kg per meter cube, both the unit get cancels, you'll get a number. Okay, a number you'll get. That gives you the specific gravity of fluid X. Okay, it is a ratio of density of any fluid by density of standard. I hope you understood these four properties. So in next session we'll discuss a few more properties of the fluid. Thank you.